welcome back to part 3 of module 3. So in this section, we're going to take a look at the different types of machine learning, the concept which we talked about in the earlier video, where we are learning the rules or the algorithm from or program from the data itself. So we are going to learn, apply these algorithms to learn some sort of pattern or some sort of rule from the data. And there are actually different types of machine learning techniques that are used. So this diagram basically shows the foremost broad groups of machine learning, and I'll try to explain each of them in turn. But in terms of industry applications, the most common ones are actually the two on the left, supervised learning and unsupervised learning. But there's another two types. One is called semi-supervised learning, and the last one, reinforcement learning. Now, AlphaGo, self-driving cars, and many of these new applications, they actually fall within the domain of reinforcement learning, a type of machine learning where we can actually learn from trial and error process. Like the example I mentioned just now about the throwing the ball into the waste paper basket game. That kind of learning is actually an example of reinforcement learning because it's able to learn from trial and error examples. And in reinforcement learning, there has been many interesting demos actually being provided, but in terms of industry applications, actually still very much in the lab stage. Okay, even things like self-driving cars, of course, there are demos of that, and people are actively doing trials of this, but it is really not in wide scale use yet. So I'm going to focus a little bit more about supervised learning and unsupervised learning, but semi-supervised learning is actually like a combination of these two. So I'll try to explain what is supervised learning followed by unsupervised learning, and then you can see that semi-supervised learning is the in-between or the hybrid of the two. So under supervised learning, you actually have two types of outputs possible. If you're trying to predict a group or a category, so the output that you're trying to guess, which is the output or target variable, is a category or class, it's a group. Then that kind of supervised learning is called classification. So for example, an image recognition, like trying to recognize the horse in the earlier example, the output is either horse or not horse, two categories. So that kind of a task, supervised learning is actually a classification problem. And in terms of application area, it could be used in, for example, medical imaging. So you have many x-rays of patients, and some of the patients have COVID, some of the patients do not have COVID. So you want to have an automatic way of classifying the x-ray picture, which is actually typically a very time-consuming and also laborious task for the radiographer. So if you can automatically recognize normal x-rays versus patients who have COVID, actually that would be a big productivity gain. But that kind of problem is actually what we call a classification problem. It's a type of supervised learning. Now, if what you're trying to predict is not a class or a group, but it's actually the number. So for example, you're trying to predict a correct price to use or a correct cost to actually set for a particular product. The output or the target variable is actually a number. It's a numeric value. It's not a group or class. Those kind of problems are called regression problems. So regression problems are also a kind of supervised learning, but in the case of regression, the output is not a category, but it's actually a target variable. It's actually a numeric, it's a continuous target variable. So it's a number. So for example, housing price valuation or housing price prediction is an example of an application area using regression algorithms. Now, for unsupervised learning, there is actually no target variable. So you do not have a known output variable that you're trying to predict. What you're trying to detect is just the underlying pattern in the data. Okay, there's no output or target variable per se. So there are two types of unsupervised learning. One is clustering, basically grouping similar data together. So for example, you want to do a recommendations for books. So if you buy this book, you want to actually find some other customer who's very similar to you so that you can recommend a similar book to that particular customer. So this is actually an example of a recommender system. So recommender systems is based on this idea of clustering, grouping together similar data. So application areas include customer segmentation. The other group of applications that are using unsupervised learning is basically what we call association rules. So market basket analysis, a type of unsupervised learning. There are others as well, right? For example, dimensionality reduction. Semi-supervised learning is a combination of two. So in the supervised learning case, you have the target variable being available. And in the unsupervised case, you have the no target variable available. But for semi-supervised, you have the target variable, but only for a subset of data. That means not all the examples that you have a target variable associated with it. Some of it is just unknown. So you have partial number of samples actually have a known target variable, but the rest of it is unknown. So in this case, you can see that it's a hybrid of the two because it's only partially known. Partially known target variables, but for the entire data set, you do not have. So the ones that you can partially know about, you can use this semi-supervised learning to sort of expand the range to include the other target variables that you do not know about. Okay, so it's a hybrid between the two. So let's take a look at a specific example to see the difference between more clearly between supervised and unsupervised learning. So assume that you are doing the image classification problem, which is a supervised learning algorithm. You have an input, and the inputs are basically pictures of these two animals, the one with the pointy ears and the one with the long nose, right? So you need to have many examples of these two animals. And you also want the algorithm to learn the association between the image and the known output that you have, the target variable. Now, this target variable is basically what we call labels, right? It's actually a tag or a label that tells us what is the correct answer for that particular example. So supervised learning works only when you have labeled data. That means you must have a known target associated with the image when you're presenting that example for the algorithm to learn from. Otherwise, the algorithm will just learn that there are two animals, but it doesn't know what's the associated label. It doesn't know what animal it is. So I'm going to present it lots of pictures of this pointy ear animal and also give it the correct label, which is a cat, so that the algorithm learns to associate the pointy ear animal with the word cat or the category cat and the long nose with the label dog. So after many training examples, if you give it a new picture of a cat, it will correctly label it or predict that the output corresponding to that picture is actually cat. For example, you have presented this animal there, and I don't give it the label, given that it has many examples of cats, it knows that this is actually a cat. It will predict that the correct label is actually cat. Okay, so supervised learning requires labeled data. Now, if your data is unlabeled, that means you have only many different pictures of these two types of animals, but you do not have the corresponding label. You do not know what type of animal it is, or you do not have examples where the known answer is given. That means I have already somebody who has tagged that particular image as cat or tagged that particular image as dog. So what the algorithm will just learn from this unlabeled data, that means there's no corresponding tag for the data, is that there are two types of animals, but the algorithm will not be able to distinguish what type of data or what type of animal it is. Now, if you have used some of this if you've used Facebook for storing your pictures, you realize that if you store pictures of your friends, it will quickly be able to group pictures, similar pictures of your friends together. So all the friends that you look like this will be grouped together. All the friends look like the other group, and the other group will look like that. However, it doesn't know who they are, right? But the moment you actually start assigning a tag for your friend, you will find that quickly you can recognize all the rest of the pictures of your friends. So what you are doing is actually providing the labeled data. So once you provide Facebook the labeled data, it will quickly be able to associate, you learn the pattern and then basically be able to auto-categorize all the photos of your friends for you. So that's the power of having supervised learning, but it does depend on the presence of labeled data. So just another picture just show you this. Okay, so I have all these animals and I give it training examples with the label. So if I pass it through a supervised learning algorithm, it will learn the association that this is supposed to be a dog, this is supposed to be a dog, and this is supposed to be a cat. So if I pass the image without the label, it will actually predict what's the correct label. So this is okay, it correctly labels that, hey, based on what all the training samples I've had previously, I know that this thing with a long nose is also a dog. This is with a long nose also a dog, and this one, even though the ears are partially hidden, the other features like the triangular nose and the big eyes also tells me that this is a cat. So it still learns that this is a cat. But there must have been training examples where the labels, the corresponding correct answer or the correct labels have been known to it. So this is actually called supervised learning, is because it is as though the person who actually provided the examples with the label is a sort of teacher or supervisor. You have already provided the algorithm. What is the supposed correct answer for each of the input? You are the supervisor. You provided the algorithm the correct label or the correct answer associated with each image. So it just learns the relationship between the two. So it is called supervised learning because of this character. There seems to be that there is a teacher or a supervisor that teaches the algorithm what is the correct association to use. However, if there's no correct label, then I just give it lots and lots of raw samples of images without the label. Then an unsupervised learning algorithm, just like you provide Facebook lots and lots of pictures, but don't tag each of the images, it will just group similar patterns together. So all those animals with the long nose, or you group them together, all those animals with the pointy ears, you group them together, and all those animals with the long neck, you group them together. And the body doesn't really know what these animals are, right? So it needs somebody to actually go and label the data in order to get the supervised learning algorithms working. So most of the useful applications like predicting housing prices or predicting whether the X-ray is actually a COVID patient or non-COVID patient, they require supervised learning algorithm. But getting the so-called labeled data is actually quite costly. Most of the data starts off in this state, unlabeled. So you actually need a lot of human intelligence to prepare the label data ahead of time so that you can actually learn the association. And then from there on, once you have the label data, the algorithms can actually very quickly pull up the corresponding correct label. Now we have this many different algorithms that we can use. You can see that different algorithms for supervised learning. One for predicting numeric numbers, which are regression, which I mentioned earlier. And if I'm predicting a class or a group, then it's called a classification problems. Now, different algorithms that we have here have different advantages. So for example, if I want very high accuracy and I'm not too concerned about the speed of the processing, then I can use things like neural networks, which is very computationally intensive, but it's great for accuracy. But it doesn't give you a whole lot in terms of speed nor explainability as well. So if you want explainable, you want the algorithm to be able to explain how the decision is actually being made. So basically things like decision trees and logistic regression are better for those, but they're not so high in terms of accuracy, right? But they're better for explainability. If you want to have very large data sets, so you need to have very high speed in doing the processing. Things like the probability based on naive based, they work better, right? So if it's not too big, you can still use either one of them. There's another linear support vector machine. So linear support vector machines, they don't work so well if your data set is very large, although they still can be a bit better in terms of speed than the neural networks. Now you have corresponding characteristic for the other side as well. For the regression algorithms, some algorithms are better for accuracy, other algorithms are better for speed. For clustering, you have different types of clustering algorithms as well. So this is an exercise, and I would actually pop over to the web to just show you what this is about. And you can try it out on your own as well. Let me just show you this one first. So in this machine learning playground, we have an implementation of several well-known classical machine learning algorithms. We have the k-nearest neighbor algorithm, which is based on the neighborhood, which is the closest examples, and it just takes the majority as the correct class. Then we have the neural network based one with one single neuron called the perceptron. We have support vector machines, and we also have decision trees and neural network. So the purpose of this exercise is to really demonstrate to you that it can learn the pattern from the data itself. So assuming that I have two types of data, orange dots and purple dots, I want to basically learn what is the correct way or the correct boundary or rule to use to divide or separate these two data. So let's make it very simple for this algorithm. First, I will basically have some orange dots over here, and I have some purple dots over on the top right-hand side. Now, if you look at it visually, you know that basically in order for me to have a boundary or division to split up the data into two sections, where one region is the orange region, so any dot inside there should be correctly be classified as the orange dot. That means it's not likely to be a purple dot. Whereas another region is basically a purple region, where any dot in that region is likely to be a purple dot. So what is the correct boundary for this orange and purple region? Now, if we look at it visually, we know that with our eyes, we can see that it is basically a backslash, right? It's a diagonal line going from the top left-hand corner down to the bottom right-hand corner. But if we want to learn the data from the, we want to learn this boundary or rule to use to separate the data from the data itself, then we can have a number of machine learning algorithms or machine learning different strategies for learning from the data. One of the simplest is actually this k nearest neighbor, which basically has a very simple rule. Assuming that I pick a random point in this space, the tree nearest neighbor, that's why it's called the k nearest neighbor, and I use the word, I use tree because the hyperparameter here is set as 3, which means that I can adjust this. So hyperparameters like this, value of k, are adjustable values for every learning algorithm that will actually affect the way it performs. So if I have a hyperparameter of 3, and I look at 3 near, so those what the closest to it will be actually 3 orange dots. Those that on the other side, near where the purple dots are, the 3 nearest neighbors will actually be purple dots. Now somewhere in between, you might actually find a case where the 2 nearest neighbors are actually orange and one neighbor, the next nearest neighbor is actually purple. So the majority would win, right? So I will still classify that point that's closer to the 2 orange dots as an orange dot because that one single purple dot is just too far away. So I click on train, it basically uses this rule of majority among 3 neighbors to sort of group the data into 2 separate regions. So you can see that actually the boundary that it creates is very much what you would actually as a human also use as a boundary to actually separate the 2 regions. Okay, so it does actually learn the general trend that you should be using. Now you can see that actually given the same set of data, if I use another algorithm like decision tree, it would actually generate a very different pattern. Right, so the k nearest neighbor, because of the way it works, it tends to generate a diagonal line, more or less following the trend. But if you use something like decision tree, it tends to generate rectangular regions, and the best fitting rectangular region at the moment, although it is actually, visually you can see that actually the corner case here, this corner here is actually a bit too close to the purple dots because it really doesn't follow the generation, because most of the orange dots are actually on the lower left-hand corner. It's not actually so high up near the orange dots. It's just that this particular rule that's being generated by decision tree tends to favor rectangular regions. So every single learning algorithm has its own bias, right? Its own tendency to generate certain patterns in the rules that it learns from the data. And before you actually make any assumption, there's actually this theorem called the no free lunch theorem, which says that before you make any attempts to actually try to fit the data using the rule, you have no idea which particular learning algorithm will work better. So there's no free lunch. You just have to try with different algorithms to see which one gives you the best result. Even simple algorithms like k nearest neighbor may actually work better than a more complex algorithm like a decision tree. Okay, so they tend to give you different shapes. Now, there's one thing about this learning algorithm. The other thing is that actually there are some problems with machine learning. For example, if I set, there's an error in the data, there's a single orange dot there. And if I set the averaging to 1, you notice that I will have this weird pattern where the data is generally a diagonal line, but you have this sudden bulge out to include that orange bit, even though it's very clear from if you look at the general trend, this is actually not a correct data point, but it's an error. Right. So in this kind of cases where you try to fit in the data as much as you can, even though it's obviously an error and it's not following the general trend, so there's no generalization or a lack of learning of the general trend, is what we call overfitting. So overfitting is actually a perpetual problem in machine learning. So if you try too hard to fit in all the data into the correct region, you might end up in the case that you actually fit the errors in as well, right? They should be treated as errors, but you fit them into the general trend as though it is actually a genuine data point. So this will result in errors. So any point that's here currently in this region will be classified as a orange dot because of this boundary. But if you look very carefully, obviously all those points that are here actually are supposed to be closer to the purple region. So all these points down here that are in error actually are considered errors only because of the overfitting. It's not because the points are actually in error. It's just that my original rule that I learned is not the correct rule. It's actually considering the error, the one single point there, as part of the data as well. Okay, so you need to detect overfitting when you're doing machine learning or training of the model. And but the good news is actually for most of these algorithms, by adjusting the hyperparameter, for example, now average over 5 values instead of 3, you can actually smooth out the data and remove the overfitting. Okay, so it's actually possible to do it, but you probably need to detect it first and then adjust the hyperparameter to make sure that you learn without the overfitting occurring. Okay, coming back to the slides. So from the exercise just now, you can see that the algorithm you use has a drastic impact on the kind of pattern that it learns from the data. So some algorithms will favor a diagonal line, other algorithms like the decision tree would favor a more a pattern that is rectangular in shape. That means there are like straight lines and there are rectangular regions in the boundary itself. Just get my laser pointer up. So you can see that instead of a diagonal line, you actually have a rectangular region here, another rectangular region here, and another rectangular region here. The complexity of the regions being generated also depends on the hyperparameter. In this case, is the tree depth. So the deeper the tree, the more fine divisions we will have in the data, and therefore it will also have a higher tendency to overfit as well. So it's always a trade-off between accuracy or how closely you follow the data. And if you try too hard, then the patterns you learn will be overfitted, right? Because you are trying to fit in even the error cases as part of the normal data itself. Like what we showed you just now with the k nearest neighbor. But good news is we can adjust the hyperparameter k, just like the tree depth, another hyperparameter for the decision tree. Now, the hyperparameter for different algorithms will be different. So for k nearest neighbor, it's just the number of neighbors k. So if I make this smaller, it will tend to overfit. But if I make it larger, because I average over a larger number of samples, the overfitting tendency is reduced. Okay, so these are some examples of the different algorithms that we can actually use. So some of it already shown you. So for first one is actually a k nearest neighbor. So in this algorithm, I will just compare the nearest samples to the new point that I have. So the three nearest neighbor, let's say I use k equals to 3, the three nearest neighbor actually one square and then two triangles. So in this case, this question mark should be classified as a class 1 or class 2. 1 class 1, 2 class 2. So the majority is class 2, so it should be a red triangle. Now, if I use k equals to 1, it will just look at the one single neighbor, in which case it will be classified as a red, as a blue square instead. So you can see that the hyperparameters like k, they can drastically affect the result. You can switch from one to the other one. But which is more correct? Obviously, if I average over more results, then actually I have more samples to look at. Is more likely to be correct because this single blue square may be actually in the wrong position. It could be an error. Another algorithm is actually a more linear algorithm, a straight line based algorithms called logistic regression. So this will actually create a new probability line where this blue line actually represents where it's 50% chance of being a blue dot and 50% chance of being a cross. So the further away from the line you are, the more higher the probability or the likelihood that it's going to be a cross. The further away from the blue line, the blue line is really the 50% probability line. That means it's a random, either it's 50-50, it's either one of it equally likely. But the further away from it, the more likely it is going to be the other example. That means it's more likely to be blue blue dot rather than a cross. So this is actually a case that we want to be as far away from this 50% line as possible to be more certain. So it's actually maximally ambiguous. But you can see that it's called a linear model because the separation line, the boundary, just like our earlier example with the k nearest neighbor, tends to be a straight line. But in this case, it's a perfect straight line. It's not even a slightly bent line. It's because of the way the algorithm works. Okay, the underlying mathematical formulation for it. Just back to the decision tree. So decision trees tends to create rectangular regions because it's actually organized as a series of if then else rules. So you can see that one division we should use is actually whether the income is below 60 or the income is above 60. And you can see that all those above 60 is sort of mixed. It's either orange or blue, but all those that are below 60, they tend to be, the majority are actually blue triangles. So I will generate one rule based on this single division of a single split. So every split that we have, every boundary here is basically a split condition. So we have a case that yes, if it's below 60, it's likely to be the triangle. But if it's above 60, it's mixed. So I need to have more splits, okay, to actually further divide. So you can see that above 60, I can have one split here for age around 27. So those that are actually below 27 are likely to be purple. Sorry, again, the blue triangle, whereas those that are above are mixed. So those that are above is mixed, so I need yet one more boundary to sort of separate that region further into a more definite group as well as the other one. So as long as it's sort of mixed up, we need to have a further boundary or further division. So you can see that this tree has a depth. The deeper it goes, the more boundaries there are, but the more boundaries there are, is also higher and higher chance that there will be overfitting. So there's a trade-off, okay, between accuracy and how much overfitting will be too much before you need to actually adjust the hyperparameters to rein in the overfitting tendency. Support vector machines, very much like the logistic, except that unlike the logistic where it's just a 50% line, they actually have a sort of a drain or a boundary. This is actually a safety margin. So for support vector machines, it will just look at the points that are closest to this boundary so that this boundary or this separation region between the two paths is as wide as possible. Okay, so it's not just finding a straight line to sort of separate the two lines, but I also want to find a straight line to separate the two lines so that I'm maximally certain, right? So there's a certain boundary or separation or margin between the two different regions for the two groups of data. So if obviously if the data cannot be clearly separated, then you find that the margin requirement cannot be met, right? So you need to actually allow for some sort of tolerance of how much deviations from having the margin that you will allow. Being too strict itself, that means 100% must be on the correct side of the border. Sometimes may not be ideal because you will have data points that are actually in error, and if you are too strict about it, you actually end up having a boundary where the margin is actually smaller than what it can be. Right? So the idea is to have that bigger gulf between the two so that there's a clear separation between the two classes. So this is one good algorithm, so the analyzes, right, support vector machines. Okay, coming down to the last few, and I'm going to talk about this in a little bit more detail because the next section is about deep learning. So for deep learning, we are using artificial neural network. So this is actually one single artificial neuron. So it's actually the structure for one artificial neuron is fairly simple. You have the inputs. Every input to your neuron has a weighted sum. That means there is some sort of weight that is changed every time the neuron learns something, right? So the weighted sum is basically x1 multiplied by w1 plus x2 multiplied by w2 plus xn1 minus times w1. So it's the weighted sum of all these values. Now, the weighted sum will be just a linear function which tends to generate a straight line. So if I want to actually have more different types of patterns on even curves that I want to learn, I need to pass it through some sort of non-linear function. So typically, it will pass through some sort of activation function or thresholding function, a non-linear function, so that we modify the weighted sum in order to emulate more different curves or shapes that we want to learn from the data. Now, one single neuron like this can only either learn a straight line or a slightly a slight curve from the straight line. It's not able to learn very complex patterns because if you have many kings in the line, this single neuron is definitely not going to be able to learn it. Like for example, you have some sort of spiral shape, it can't be done with one single neuron. However, just like our brain, we don't just have one brain cells, but we have many brain cells, and all these cells are actually interconnected to each other. The power of the ability of the brain to learn is actually the same as the neural network. It's actually in the connections, right? The connections would adjust the weights, and we are actually arranging them into layers. So the first layer is called the input layer. The last layer is the output layer. Any layer in between is what we call a hidden layer. Now, is this actually a simplification? Because in the brain itself, the neurons are not laid out in a straight line or in a 2D arrangement like this. They actually spaced out in 3 dimensions, right? But in order to make it implementable with our computers, we have a simplification. It can still learn very complex patterns, okay, which is why neural networks are actually the algorithm of choice for things like deep learning today, because they can actually have very remarkable results in terms of their learning capability. So for deep learning network, it's nothing other than this simple artificial neural network or ANN, but with many hidden layers. So a typical deep learning neural network will have 10 or more of these hidden layers. Traditionally, neural networks, when they were first invented, only have 1 or 2 hidden layers. But today, with the artificial neural network being used in deep learning, the number of hidden layers has grown up to above 10. And for very complex deep learning networks, they can go into thousands. You need to have huge computational power to actually process it when there are more layers, because it's not a multiplication in terms of growth. It's not additive, nor is it it's actually a geometric increase. It's to the power of as you have more layers. So having 2 layers will be more complex. Having 3 layers is not 3 times more complex. It's actually many times. It's to the power of 3, right? It's a geometric increase in terms of the complexity of the computation. So having 10 layers will really increase the number of computations required very quickly. And we actually come to the end of this section. So the next section, I'll deep dive into deep learning a little bit more. So thanks for your attention. I'll see you in the next video.